end. I mean, it's 11:35. The goal is to end at 12:35. It is possible, because I would like to make a mad dash to get back on schedule and cover both dark energy and baryogenesis today. It's possible. I just want to warn up front that I may spill over by 10 minutes. But I'm going to make up for that by the extremely good use of time that I use in the rest of the lecture. You'll be really impressed with me. There will be no dilly-dallying and talking about random stuff like what I'm doing right now. OK. So today we want to talk about basically the cosmological constant problem, or the vacuum energy problem. And then we're hopefully just going to get a 15-minute blast of baryogenesis. You're just going to get everything you need to know about it in 15 minutes. And then that little kernel of knowledge will expand into a large piece of popcorn inside your body as you age. And sometime when you're 37, you'll thank me for what happens at the final 15 minutes of this lecture. OK, so seriously, I've been forgetting to tell a joke in the middle of almost every lecture. But I have a killer joke not by me. There is no excuse for us not telling it during this lecture. So if we get to the halfway point, if we get to noon, and I haven't told a joke yet, someone who is going to be in charge of stopping me? Thank you very much. OK, so first of all, why is the cosmological constant problem also known as the vacuum energy problem? So let's just that part is easy. So the action for general relativity, the Einstein-Hilbert action. There's the gravitational part. I mean, the Einstein-Hilbert action is the gravitational part. Okay. So this is the Ricci scalar minus 2 times the cosmological constant over 16 pi g Newton. And then we're supposed to add to that any matter Lagrangian that we think is correct. And then we vary this thing with respect to g mu nu, and we get Einstein's equations. G mu nu, that's coming from varying this guy. And then we get plus the cosmological constant term, lambda g mu nu. That's coming from varying this term. And then equals 8 pi g Newton T mu nu, where T mu nu is the stress energy tensor that's obtained by varying this term with respect to the metric g mu nu. At the level of the equations of motion, the point is just that we can drag. We're always free to just drag this term over to the right-hand side, cross it out over here, and just absorb it into the definition of the stress energy tensor. So we just define a new stress energy tensor that includes a contribution which is minus lambda over 8 pi g Newton times g mu nu, so that now the new right-hand side just becomes, just has the new stress energy tensor that's incorporated this term. So why is that thing called the vacuum energy density? Well, that's most easily seen if we take L matter here. So let's replace L matter by the let's take an example for L matter. The simplest example we can think of is a scalar field. Okay, so I'll replace L matter here by the kinetic term and the potential energy term for a single scalar field phi. Okay, so I haven't told you what the potential term is, but it's some function that's supposed to be bounded below. So it's some function. Who knows what it looks like? But it has a minimum here. And the vacuum state of this system is where the potential is where the scalar field is a constant everywhere in space and time and is sitting at the minimum value of its potential energy. That at least classically speaking, is the lowest energy configuration of this potential. So you know, I can think of this potential as this potential. Sorry, the whole point of this potential was that it was supposed to. Even there, I didn't do it correctly. The whole point of this potential is that it's supposed to have exactly the same shape as this potential, but just shifted up so that the minimum is exactly at 0. And then this offset here, if the real potential is shifted down like this by some constant V vacuum, that offset from 0 energy is known as the vacuum energy. For obvious reasons, it's just the energy of the lowest energy configuration. It's the energy that's still there even if you make the field completely uniform so that it has 0 kinetic energy and sitting at the lowest point in its potential so that it has the lowest possible potential energy. You know, in classical physics, shifting the potential of some classical field or some classical particle in classical non-gravitational physics, that has no effect. But in cosmology, it does, because you know you can see that if I write this potential as this potential, so let's call that v prime of phi. Well, not the derivative of phi. Let's call that v twiddle of phi, the potential whose minimum is at 0, plus v vacuum. So our full potential v of phi, if we write it that way, you notice that so v vacuum here is just a field-independent constant. So we get a constant term in the action here, and then we have this other constant term, minus 2 lambda over 16 pi g Newton. We have two terms that are both just constants in the action. There's no physical distinction between them at this level. It's entirely a matter of definition. How much of that, we can split up that constant and call as much of it we like lambda, and as much of it we like the constant contribution to v vacuum. But then when we ultimately go and calculate physics for this theory, we can't somehow physically disentangle that splitting. It's all just a constant that we've added to the action that we then plug into, that we then use to derive the equations of motion or plug into Feynman's path integral or whatever. So, the point is these two things are redundant. So I can always, as a matter of convention, choose to set this part of the constant to 0 and reinterpret every constant contribution as a shift to the vacuum energy, or vice versa. So anyway, that's why these two things are, so it's a problem. So there's something we don't understand. There's some things I'll explain. We don't understand really what's going on here. But according to the current understanding, the distinction between the cosmological constant and the vacuum energy is a matter of convention. Okay, so we have observational evidence that we have to add such a positive vacuum energy, or in other words, a positive cosmological constant, to the equations of motion, to the Friedmann equation, in order to match the observed evolution of the universe. Okay, so remember, if we write it in terms of the cosmological constant, so let's arbitrarily let's imagine that we set all the other potentials to 0 in their minima to 0 in all the different fields in our theory, and we write the constant out explicitly as the cosmological constant. Then in that language, we have evidence that we need to add a term like this to the right-hand side of the Friedmann equations. Okay, so what is the nature of that evidence? Well, first of all, let's go back to before 1998. What was the status then? astronomers went out and tried to make a tally of how much. So astronomers did two things. First of all, they went out and they measured the value of the Hubble constant, how fast the universe is expanding today. And they used that to calculate the critical density today. Okay, so they got a number. They got an estimate for what this guy was. And again, that's the threshold where if the density was bigger than that today, the universe would be closed with k equals +1. And if it was less than that, the universe would be open with k equals -1. But okay. Meanwhile, they alternatively went out and they tried to make a census using a variety of different techniques of the total amount of matter, non-relativistic matter in the universe. So that includes baryons and dark matter. And they found and they insisted that they knew what they were doing, that the matter density that they found when they added up everything was only about 30% of the critical density that they estimated based on the Hubble constant. Okay, and so why was that a problem? Well, there were sort of two things at the time. There was an observational and theoretical conundrum to be resolved. So, if they were right, so if what the universe consisted of today was there was this guy, which was entirely just non-relativistic matter, baryons and dark matter, with a density equal to 1/3 of the critical density, and nothing here. So no, people at the time were not thinking about this. Did not include this guy in the Friedmann equations. Okay, and then to make up the difference, k would have to be -1 to get the two sides of this equation to be equal. So they had an open universe with a certain predicted amount of matter density in it, non-relativistic matter density. So in such a universe, you can solve the Friedmann equation and convert the measurement of h0 into a measurement of how old the universe was. When in that model was the Big Bang? How long ago was it? And so they found that the age of the universe today, according to that model, was, I don't know the exact number, it was something like 8 billion years old. And the problem was that, on the other hand, astronomers, another thing they do, which is sort of entirely decoupled from cosmology, is they have developed quite good, they're quite good at understanding the evolution of populations of stars. And so if you give birth to a bunch of stars, let's say a bunch of stars collapse and begin shining out of a gas cloud, they emit a certain spectrum, and then as the stars age at different rates, that spectrum evolves in time. And by looking at a collection of stars and observing their spectrum, you can estimate how old that population of stars are. And in particular, our Milky Way, or every galaxy, but in particular our Milky Way, is surrounded by a bunch of so-called globular clusters, which are little, very dense clusters of about 100,000 stars. And these guys are important because they are much older than the Milky Way galaxy. These guys formed a very long time ago. And so they went through and globular cluster by globular cluster used these stellar modeling techniques to estimate their ages. They found some that were older than this. So they found some that were 12 billion years old, 13 billion years old. Okay. So in other words, according to the standards of the time, according to this estimate, those globular clusters appeared to have formed before the Big Bang. Looks like a problem. So this cosmologists tend to dismiss estimates like this from sort of astronomers as being too messy to take seriously. They sort of are like, oh, they must just be fudging something, or there's so many uncertainties in those calculations. I'm sure that a difference of only 50% here, probably will just iron out in the wash when they do their calculations better. And same with this claimed observation. Anyway, but these guys were right. Both of these guys were right. So even at the time, okay, so that was the observational conundrum. The other thing is just that, so we'll discuss this more next week when we meet inflation, but you know, at the time it was already a big puzzle, theoretical puzzle. Why was the matter density today, why was the total energy density of the universe so close to the critical density? Because if the universe really is full of just matter and radiation, then as it evolves, if at any point it deviates slightly from the critical density, then as the universe gets older, it should deviate more and more from the critical density. So why was it still, why at this late stage in the universe's evolution was it still equal to the critical density within a factor of 3? That meant it had to be astronomically close to the critical density at earlier times. You know, from a theoretical standpoint, most people thought that, well, there must be some physical mechanism in the early universe that set this to either exactly, set the density in the universe either exactly to the critical density or exponentially close to the critical density, in which case we would expect, it would be sort of shocking if we happened to, if it only began to be deviating today. We would expect to see it still equal to the critical density today. And indeed, that's one of the things that inflation was invented to explain. So anyway, on those grounds, most theorists thought that the critical density should be exactly equal to the critical, that the density today should be equal to the critical density, not 30% of the critical density. And so, again, on theoretical grounds, there were also reasons to believe that maybe there was something else out there that was bringing this value up from 30% of the, bringing the total energy density of the universe up from 30% to 100% of the critical density. Okay. So that was the so-called flatness argument or flatness problem. Nevertheless, and so there had been papers, you know, already in the earlier papers in the mid-90s arguing that there should be a cosmological constant to resolve those problems, but they did not, you know, get that much attention. And the real event was when two different teams of observational astronomers measuring supernovae, a certain type of supernova, these type 1a supernovae. So these have the property that astronomers think they're very well calibrated objects, so that based on local observations, they, by looking at the spectrum of these supernovae, they can determine quite accurately by astronomical standards what the intrinsic luminosity of the supernova is. And so again, it's just like if I tell you I have a 100-watt light bulb and now you look at it and you see how bright it looks to you, you can estimate how far away it is from you. You know, if I tell you you have a supernova of a certain particular luminosity, by observing how you can observe how bright it looks to you and make a measurement that way of its so-called luminosity distance. How far away is it from you? And you can also measure its redshift. You can also just measure, it has various recognizable spectral lines recognizable from laboratory experiments on Earth, but they're all shifted by some common factor because they redshifted on the way to us as the universe expanded. And so you can plot the sort of factor by which, so 1 plus z is just the common, z is commonly called the redshift by astronomers. 1 plus z is really nothing but the ratio of the scale factor today to the scale factor at the time that the thing was emitted. And so in other words, this is 1 plus z is the factor by which the recognizable spectral lines of hydrogen, let's say, will be shifted to longer wavelengths if they were emitted at an earlier epoch when A was smaller than it is today. So anyway, basically, you can, for different solutions of the Friedmann equation, you can plot a predicted curve of luminosity distance versus redshift, and you know, there's just various, you know, depending on whether you assume, okay, the universe is entirely, it really is 30% matter, and then there's no cosmological constant, or or it's 100% matter and there's no cosmological constant, or there's 30% matter and 70% cosmological constant. You can, for each of these, there's a different curve here. To make a long story short, the supernovae lie along the one that has omega matter as 0.3, that says that the matter density in the universe is 0.3, and the cosmological constant makes up the remaining 70%. Okay, and at the time, those observations were kind of ratty, and they've just gotten better and better over time, and so it's quite a clear observation at this point. And then also, just being in the interest of just being very brief, since then there's been dramatic progress in making detailed measurements of the cosmic microwave background, and in particular of this temperature power spectrum of the cosmic microwave background that we've talked about. And again, just to make so again, the current story is that you as Kendrick mentioned in his talk, in order to fit this curve, we need 6 parameters basically, which 6 physically different parameters that are these days best determined exactly from fitting this data, and those include the density of matter, the density of baryons, but one of the amount of the primordial spectrum, but and the universe in those fits is taken to be flat, or you can let that parameter float. I'm saying this in a convoluted way. I haven't introduced you to all these parameters yet, but there are 6 parameters you need to fit this guy. When the dust settles on those 6 parameters, they exactly confirm this fact that the total matter density is about 30% today, or maybe 30, 35, 30, and the dark energy density is 70% of the critical density. Okay, so those are our 2 main lines of evidence at this point. That there's sort of the supernovae on the one hand, and by now there's really the CMB, which is by now entirely on its own, independently drives you to say that by far and away the best, a fit with no cosmological constant is extremely disfavored statistically relative to a fit with cosmological constant. And then the more extra data you include, if in addition to just using the CMB, you analyze the CMB together with supernova data, or you analyze the CMB together with measurements of the Hubble constant, or you analyze it together with measurements of the distribution of galaxies, and in particular the so-called baryon acoustic oscillations in the distribution of galaxies, which again is something we haven't talked about. But there's various different observations that you can combine the cosmic microwave background with to make, and in each case there's a consistent story that this evidence for 70% of the universe in dark energy gets confirmed more strongly. In the interest of time, that's all I was going to say about the evidence. Now let's just say a word about there are now sort of 2 independent problems presented by this evidence, which go under the name of the old cosmological constant problem and the new cosmological constant problem. Okay, actually, it's a perfect time to pause for a joke, I'm proud to say. I remembered. Okay, this joke comes from a member of this class who does or does not want to be named. I forgot to ask. I don't want to look at the person in order to not out them. I hear nothing. So this is an anonymous joke submitted to me from the class. The joke is, why can't mountain climbers get mosquito bites? Sorry? No, you don't have to. The answer is because you can't cross a scalar with a vector. Who? I think that is a good joke. By my standards, that is a killer joke.
It's my joke, guys.
Okay. Also, it set me on. I won't even drag you through all of the. For some reason, it made me make to myself a million much worse related jokes, like, why does nobody mess with Captain Ahab or the ghost of Hamlet's father? Because you can't cross a whaler and a specter. It's worse. Or okay. Anyway, I love that someone gave me a joke. I hope you'll give me more jokes. Okay, the old and new cosmological constant problem. So the new one is easy to state. It's the thing we've drawn already. We draw this. We make this plot of the current best fit to the data, and plot what is the, according to the fit, how much of the universe as a function of as it expands, how much of it is radiation, how much of it is non-relativistic matter, and how much of it is vacuum energy. And at early times it was radiation dominated, and at later times it was matter dominated. And then at very late times it has been vacuum energy dominated. And again, we happen to live at a moment when the vacuum energy density is only bigger by a factor of 2 in comparison to the matter density, even though they're scaling very differently with the scale factor. So the scale factor has, over the region of evolution that we even over the region where we think we understand very well what's going on, the scale factor has evolved by a factor of 1 billion. Meanwhile, as A changes by a factor of 1 billion, this guy is decaying as A to the minus 3. This guy is going as A to the 0. So it seems like kind of on order of 10 to the minus 27 coincidence that we happen to be located right at the moment in time. This factor of 1 billion is from Big Bang nucleosynthesis to today. I mean, it's who knows exactly what. It's a bit hard to make precise this conundrum, but we live very close on this log A plot to the crossing of these two guys. I mean, much closer than my diagram really kind of exaggerates the difference here. We live very close to it. Yeah. So that's the new cosmological constant problem. Why is that the case? So the old cosmological constant problem is one that people have been wondering about for a long time, which is just that quantum field theorists, so you give them a potential, right? You say, okay, the potential is the bare potential for this scalar field, let's say, and the Lagrangian is some m squared phi squared term, and then some plus lambda phi to the 4th term, and then maybe you give them more terms than that, or maybe if you're giving them a normalizable theory, you don't. So let's say that's the bare potential, but then there's the there's the quantum effective potential, which is the thing that actually governs the evolution of the vacuum of the expectation value of these fields. And there's kind of a well ironed out technique for calculating the quantum corrections to these to the various parameters in the model. And it's very well tested in other contexts that this technique of calculating loop corrections to things in quantum field theory is correct or works well. But so in particular, you draw for every loop diagram you draw. So let's say this one has 2 external lines, since it has two external phi lines, when I evaluate this diagram with 0 momentum on the two external lines, that will give me a correction to, for example, this diagram will give me a correction to the coefficient of the phi squared term because we have two phi's on the external lines. Or if I drew a diagram like this with 4 phi's on the external lines, I would get a correction to the lambda phi to the coefficient of the phi to the fourth term. And so, this rule, if you consider all of these diagrams that contribute to the phi squared term, all these guys with two external phi's here, you can see basically how these contributions will scale with the UV cutoff of the theory. So, like this guy, for example, we have one loop, so we're going to have one, at the end of the day, one unknown momentum here, that loop integral that we have to do. So we have a d4k. And then we also have a propagator, this propagator. So there's a 1 over k squared. So when you integrate this thing, it diverges. But if you cut the momentum off at some momentum cutoff lambda, if you only integrate up from 0 to k is less than lambda, then on dimensional grounds, this integral will go like the cutoff squared. And then if you just, no matter how many bubbles you add here, if you just go through, you keep getting more and more loop integrals and more propagators, so that at the end of the day, all of these contributions all go as lambda squared. Now, if you just apply the same logic, and according to quantum field theorists, one is supposed to do that to bubbles with no external lines, those should be the quantum corrections to the constant term in the potential. And so, like, take this guy, for example. It has two loops, so you're going to get two loop integrals, d4k1 and d4k2. K1 and k2 here. And then you're going to get two propagators, one here and one here. So 1 over k1 squared and 1 over k2 squared. So this guy is going to go as the cutoff. So we have 8 powers of k in the numerator, 4 in the denominator. So this guy is going to go as the cutoff to the fourth power. So, the cutoff is usually taken to be some physical scale at which you expect the theory to break down. Now, in the case of gravity, it's because this is really a term that when we add it to the action, we don't see its effect until we're talking about gravity, until we take the metric to be dynamical and we vary the action with respect to the metric. But in the case of gravity, we think that we understand gravity. If we sort of estimate at what point the gravitational force becomes comparable to the other forces, and we expect quantum mechanics to become important, that's supposed to be the Planck scale. So if we put in the Planck scale here, we get a number. We get a predicted quantum correction to the constant term in the potential. And the bottom line is that predicted term, if you plug in the Planck scale here, is 120 orders of magnitude bigger than the observed constant that we get from fitting to the supernova and CMB data. And so, barring some cancellation between the quantum correction and the bare constant contribution in the action, and we don't, if there's some good reason that they should cancel, we don't know what that is. This looks like a pretty bad problem, that the predicted value is so much bigger than the observed value. I should also just say, physically speaking, there is just a simpler physical way to say what's going on here, which is just that, if we impose a cutoff, that's like saying we're going to say, saying we can't observe, saying we will cut off or we won't speak about momenta above the cutoff scale lambda is saying that we're not going to talk about distance scales smaller than 1 over lambda. And so it's like we've divided up space into little boxes of size lambda, of length 1 over lambda on a side. So the volume here is 1 over lambda cubed, and we're going to sort of think of those as the fundamental pixels into which space is divided. If you want to understand what's going on size scales smaller than those pixels, you need to know more than just classical GR. But then you remember from quantum mechanics, if you try to put a particle in a box of size r, that the ground state of this ground state wave function, and so if this is my potential v of x here, that it's 0 from x equals 0 up to x equals r, and then it goes to infinity everywhere else. So the ground state wave function of this guy has, there's energy in the ground state. The ground state has some positive energy due to the 0-point energy. Basically the uncertainty relation. We've put a limit on delta x, and so delta p by Heisenberg's uncertainty relation has a lower limit on it. And so this thing has some kinetic energy in it. And that explicitly, the solution of this wave function has an energy which is like 1 over r. Since r is 1 over lambda, its energy is exactly lambda. So the energy density here, the ground state of a degree of freedom confined to this pixel is lambda, and then the energy. So there's lambda is the energy per box, and then the density of boxes in space is this is the volume of the box. So the density is 1 over that. So we have lambda times lambda cubed is lambda fourth. So that's physically where this lambda fourth is coming from. Just that if we try to that's where the divergence of the vacuum energy is coming from in the first place. That according to quantum field theory, there's an independent degree of freedom at every point in space. There's an infinity of guys, each of which has some fundamental vacuum energy. And even if we try to smear that out and focus on a finite density of degrees of freedom per unit volume, still we get a huge contribution that diverges in the limit that the size of the pixel goes to 0. So I don't know. There are a lot of proposed explanations to these two different problems. I wasn't really going to cover them because there's none so far that has risen to the level that the community is like, oh, that one is probably right. I would basically just say this continues to be a vexing problem without a good solution. Now, okay, so then let me just say a word about. I did just want to say a word about modified gravity.
How does supersymmetry help? What's the story for supersymmetry?
Well, so normally the idea was going to be that so in principle, supersymmetry helps because you get, for every one of these loop diagrams, you in the limit that if supersymmetry is unbroken, you get, for every bosonic loop, you get, for every loop where a boson moves around the loop, a fermion moves around the loop, and there's a relative, and those loops give the same answer with a relative minus sign in the UV, and so they cancel. Now, in actual nature, supersymmetry is broken, and so instead, so instead of having particles and superpartners with exactly the same mass, it appears to be an observational fact that we have the particles of the standard model, and then if there are superpartners, that they are at a different energy scale by something of order a T EV, at least. So then if you take that to be the case, then those loop diagrams cut off at the TeV scale, roughly speaking. So if partners and superpartners differ by some energy scale, then once you go up to once you follow the loop momentum up to momenta that's huge relative to the splitting that as far as that huge momentum scale is concerned, the two particles really are approximately degenerate in mass. The same cancellation holds, and so at the end of the day, that cuts these loop integrals down from the cutoff scale to whatever power to the mass splitting to whatever power. But so if the mass splitting is only is of order the electroweak scale, 100 GeV or TeV, then that's helpful for explaining the Higgs hierarchy problem. Because in other words, there's already a question in the standard model about why the m squared phi squared term, where the coupling constant in the m squared is observed to be 100 GeV, when the cutoff scale could be so much higher than that. And so supersymmetry could still be helpful for that problem. But if you plug in a TeV to the fourth instead of the Planck scale to the fourth, over there you're still off by 60 orders of magnitude relative to the observed cosmological constant. So it wins you, it gets you closer, but you're still very far away. Even if you put in the electron mass there, the lightest mass scale in the standard model, the lightest non-neutrino mass scale in the standard model, you're still a long way away. Yeah, so, okay, now I really just want to say something very briefly about modified gravity. That, first of all, about MOND, for explaining galaxy rotation curves, historically the first, so as I mentioned previously in the last lecture, we have these two puzzles, dark matter and dark energy. Together they appear to account for 95% of the energy density in the universe today, whereas we, in our periodic table, account for a piddling 5%. And, it continues to kind of be an annoying issue that despite a lot of different proposals for how we might detect dark matter and or dark energy more directly, we still only see them via their gravitational effects. It's strong motivation to ask whether maybe our cherished theory of general relativity, successful as and beautiful as it might be in the solar system, maybe it's breaking down on scales larger than the solar system, or on cosmological scales. Yeah, so in particular, we mentioned there was this for galaxies. There are these if you measure how fast the stars are whirling around in the galaxy, measure their speed, their rotational speed as a function of their distance from the center of the galaxy. The prediction based on the sort of amount of stars that you see in the galaxy is that it should look like this. And the observations are that it looks like this. So the first proposed modification of gravity to account for that, to say that really there's no matter beyond the stars, but Newton's law is just modified, is what's called MOND. It dates from the early 1980s, and it's basically the proposal that around a spherical source, okay, there's basically some modification of the Poisson equation, but the upshot is that when you solve it around a spherical source, if you're close enough to the source, that there's some new constant in the modified Poisson equation, and the constant has units of acceleration. And if you are close enough to the gravitating mass, that your acceleration is that Newton's law predicts that your acceleration is bigger than this new constant, the solution reduces to the solution of ordinary Poisson equation. You get the ordinary Newtonian force law. But at larger, when the acceleration drops below if the acceleration that would have been predicted by Newton lies below this acceleration, there's a correction to the force law which falls off less rapidly as a function of r and ends up predicting this constant this constant velocity as a function of radius very simply. It also has a bunch of other successes in galaxies. It also seems to do a better job. I mean, it seems to give a much more simple, direct prediction of a property of galaxies called the Tully-Fisher relation, an observed empirical property of galaxies, than the cold dark matter model does. So in galaxies, MOND looks pretty good. You know, the main issue is that, first of all, even when you go to clusters of galaxies again are places where we see dramatic evidence for dark matter in addition to baryons, in addition to normal stars. There, MOND does not appear to fit the data. And then the biggest thing, according to the modern perspective, is that, you know, in cosmology, it's like to zeroth order the cosmology these days, you know, there's one observation you're supposed to fit. There's one observation that is just so much more accurate and powerful than everything else that if you don't, it's the zeroth order thing you start with, not galaxies these days. And that is the cosmic microwave background. And the bottom line is that MOND is this non-relativistic theory that is a modification of the non-relativistic Newton's law. It has not, to the present day, been given a satisfactory relativistic completion that can predict the early universe, and in particular the cosmic microwave background spectrum, in the same way that the lambda CDM model can. So it's kind of like a tantalizing hint on galaxy scales that maybe this thing is on the right direction, but it's still, you know, still in need of some cosmological completion to make it. So it really is true that it arguably does a better job with galaxies than lambda CDM. And that may be an important clue and in need of some extension. Now, the other modified gravity thing I wanted to mention is that, you know, roughly speaking, unfortunately, although the evidence has become, in some sense, you know, clearer and clearer, the error bars have shrunk and shrunk. Yeah, Karen.
What does MOND have to say about the bullet cluster?
Yeah, that's another thing. So I'm actually going to talk about the bullet cluster in 1 second. So let me get to that. That's my one slide I was going to show. So suddenly, between, let's say, 1998 and 2003, it became clear that the best fit that we have, the simplest model that gives a reasonable fit to the data was this lambda CDM model, this model based on adding 25% of cold dark matter that doesn't interact with anything, and then a cosmological constant with a certain value. And since then, roughly speaking, every subsequent observation has been consistent with that model, and all that's happened is that the error bars have shrunk. There's sort of been nothing. In a sense, it's been a little bit boring. There's been the picture has clarified. You know, we've gotten better and better glasses with which to view the universe, but we haven't uncovered something qualitatively new for about 15 years now. And so, you know, everyone continues to hope that as you view things with better and better resolution, collect more and more data, that you'll get new surprising clues that'll shed some light on what's up with dark matter and dark energy, just as these were surprising clues that came from more and more detailed observations. But so far, that has not happened. There's a period of sort of, so that hasn't happened. On the other hand, and now in modified gravity, there has been an actual breakthrough, which was just a couple of years ago in 2011, where an old problem was finally solved, which is that you know, for every other type of theory, for fermions, for scalars, for vectors, theories come in two varieties. Wigner, back in the day, he said particles are nothing but various different types of irreducible representations of the Poincare group, basically the Lorentz group plus translations. And he classified those, and you have certain, basically the classification is, well, there are the massless representations and the massive representations, and then each of those can come in different spins, 0, half, 1, 3/2, etc. And so up to so for all the other spins of particles, we've been able to find sensible theories of them that are both massless and where the particle is massless or massive. So we have a theory of what a massless fermion looks like and a theory of what a massive fermion looks like. For GR, that was not the case. So GR is a theory of a massless spin 2 particle. For, ever since the birth of GR, pretty much, people have been trying to find the theory of a massive spin 2 particle, massive general relativity. And for there are these anyway. It's been hard, and there were even no-go theorems that you couldn't do it. There's a famous Boulware-Desert argument that that said basically, okay, you can write down the free quadratic approximation to that theory, but then as soon as you include interactions, as soon as you let the graviton interact with itself, like it does in GR, not be just a purely free theory, you'll get an extra degree of freedom, which is ghost-like. Basically, has the wrong sign, has negative kinetic energy, and that ends up violating unitarity when you quantize it. So there was this traditional problem that you couldn't write down even a theoretically consistent model of massive gravity. Anyway, so that was solved. That argument turned out to be wrong, and the class of theories was found in 2011. And then, as people have understood it better, it's been good. It's gotten sort of more and more beautiful looking. So that nowadays one can say the following: that it's easiest if you work in sort of this Vierbein language, which if you haven't seen it, don't worry about it. But anyway, so I believe that the people who took Ruth's course, Ruth did things in this language, but. Oops. So, in terms of the Vierbein 1 form, this thing roughly this is some 1 form where its square is the metric. So this is something like the square root of the metric. The Einstein-Hilbert action. And then there's this curvature 2 form. Okay, so so there's the Vierbein 1 form, which if you expand it out as a 1 form looks like this. And so the idea here is that this thing is related to the metric by the fact that if you take 2 of them and you contract their so-called tetrad indices, this is a tetrad index, this is a space-time index. If you contract their tetrad indices A and B with the Minkowski metric, then their remaining space-time indices just give you give you back the metric. So this thing is roughly speaking the square root of the metric. And then there's the curvature tensor, which can be obtained from these guys, which is a 2 form. And if you expand out that 2 form explicitly, this is really nothing but the Riemann curvature tensor. So in this language, the Einstein-Hilbert action, the term that is just the integral of R over the manifold, this thing is the integral of the 4 form RAB wedge EC wedge ED contracted up with the totally antisymmetric tensor ABCD. And the cosmological constant term in this language is nothing but the 4 form obtained by just taking 4 vierbeins and contracting them, again, with the totally antisymmetric tensor. Now, in general, in an arbitrary number of dimensions, it turns out that if you want to write down all of the terms, so these are sort of the 2 relevant terms in 4 dimensions. There's one other. So what I want to say is that, so in 4 dimensions, suppose we played the following game. The 2 basic objects you're allowed to build your action out of are the curvature 2 form and the tetrad 1 form. And your job is just to write down any 4 form you can, so you can integrate it in 4 dimensions. Contract up all the tetrad indices with epsilon a, b, c, d. Just build me every object you can think of that way. And those are all the gravitational terms you're allowed to write down. Those are precisely the gravitational terms you're allowed to write down in n dimensions, such that when you vary them, you get a second-order equations of motion and no ghosts, like you do in general relativity. So if you followed that, if you just try to do that exercise in 4 dimensions, you find that, well, the only things I can build that are 4 forms, like this guy. This is a wedge product of 4 different 1 forms, so it's a 4 form, and has 4 different tetrad indices that I can contract up with the epsilon tensor. The only things I can do are this guy, which turns out to be the cosmological constant term, this guy, which turns out to be the Einstein-Hilbert term, and this guy, the wedge product of 2 curvature 2 forms. This guy is the so-called Gauss-Bonnet term. It's topological. It turns out to not contribute to the equations of motion in 4 dimensions. But now, if I redid the same thing in 5 dimensions, for example, I would find that I could write down a term that was built from 2 curvature tensors and a 1 form, and I contract all those guys up with the epsilons. Or I could use 1 curvature tensor and 3 vierbeins, 3 1 forms, and contract those up with the epsilon tensor. Or I could write down no curvature tensors, sorry, and just 5 1 forms: E, wedge E, wedge E, wedge E, wedge E, A, B, C, D, E, and contract that up. Okay, anyway, so there's this simple, and again, so this would be the cosmological constant term in 5 dimensions. This would be the Einstein-Hilbert term in 5 dimensions. This would be the Gauss-Bonnet term in 5 dimensions. So there's this simple rule when you have a single metric that for writing down all of the sensible gravitational terms you can in an arbitrary number of dimensions. It's a very, very neat and elegant result. All of these theories give rise to massless theories of a spin 2 particle. And so this is not how it was originally discovered, but something that was subsequently pointed out as the new theory that was discovered in 2011 was understood better, is that the story is exactly the same. The only difference is that now, just to let yourself, instead of just having 1 vierbein, let yourself have a second vierbein, call it E bar. And instead of just the curvature associated with this vierbein, let yourself have there's a second curvature tensor associated with this vierbein, R bar. So, but now, otherwise, just play the same game. Just write down any old action you can think of based on these, built from these 2 forms, these 2 1 forms, such that when you write them down, you get a 4 form in 4 dimensions, let's say, and you can contract up all 4 of the indices with the epsilon tensor. Write down all the terms you can that way. Those are all the sensible terms you can write down. But now you discover that when you perturb this theory around flat space, it's just like in the one metric case. There's no ghosts. The equations are second order. The theory is consistent. But now the spin 2 particle is massive when you've included 2 or more different vierbeins. So anyway, it's kind of a beautiful answer. And as I say, it's too early. Oh, I should say, by the way, So this theory was discovered. Again, I think that's an important discovery. That was discovered by Claudia de Rham and Andrew Tully and Gregory Gabadadze. Claudia de Rham and Andrew Tully, it's important to mention, first of all, it's important to mention that they were PI postdocs. Unfortunately, they had left PI right before they put out this paper, so it was like, ah. But they're back visiting for this semester, so there, you can see them at lunch if you want to ask more questions about this. It was really this guy, Kurt Hinterbickler, who's a postdoc here now, figured out this whole more beautiful statement of the story. And yeah, you know, so this is a very interesting thing. It's really, I would say it's not yet clear whether, I don't really have time to say why you might hope that it's related to these various problems, except to say that you do. And it's to my view the best, you know, the biggest advance in terms of finding a nice alternative to ordinary general relativity. If you want to explore, could cosmology be telling us that general relativity is modified? Yeah, I think that's all I wanted to say about that in general, except to say that there is a really great puzzle, which is unsolved, which I want to recommend to you as like one of the best open problems in physics in terms of its importance and the fact that although a small number of people have thought about it, it's basically a new problem in the grand scheme of things, and essentially nobody has thought about it in the grand scheme of things. And so that is to find, so there is a hope that among this category of, among this category of modified gravities, there is a theory. So those are called massive. That's sort of the general framework for massive gravity. I'm actually not bothered by that, but I know that there are people in the world who go crazy when Chuck squeaks like that. Is anyone going crazy from that? Anyone? Okay, in that case. It's hoped that within that category of theories, or maybe by some clever modification, there are these so-called partially massive theories. So what are these guys? So as I say, Wigner classified the different representations of the Poincare group, the different representations of the particles could live in around flat space. And again, he categorized it. He found that there were the massless particles and the massive particles. And in each case, you could have some spins, 0, 1/2, 1. And in the massless case, whatever your spin, the number of different helicities, the number of different helicity states you can have is 2, whereas in the massive case, it is 2s plus 1. Okay, so the massless graviton has just 2 polarizations, plus and cross. A massive graviton is supposed to have, so this, where spin is 2, a massive graviton is supposed to have 5 different helicities, plus and minus 2, plus and minus 1, and 0. Okay, now that is if you classify things around Minkowski space. If instead you do the same classification around de Sitter space, in other words, around an accelerating universe like the one we appear to be entering according to the data, then the classification changes slightly. So there's a new parameter, which is the cosmological constant that sets the curvature of that de Sitter universe. And so now, when in the vanishing mass case, the classification is basically the same. In the case where m squared is not 0 and larger than 3/2 lambda, you get the same answer as you get in ordinary Minkowski space. But then there is the critical case where m squared is equal to 3/2 lambda, in which case you get a special new sort of representation that you don't see from the flat space analysis, which has only where a spin s particle has only 2s degrees of freedom. So this theory, compared to this one, has an extra gauge symmetry that eliminates the helicity 0 mode, chops out this +1, and leaves you with only 2s degrees of freedom. So why is that interesting? Well, it's interesting for a bunch of reasons. So first of all, this theory, if you find it, is the first example of a theory where it can have a cosmological constant that is small, and the smallness of its cosmological constant is protected by a symmetry. So normally, if you have a small parameter in physics, you don't worry about it if you know that there's some symmetry reason why it either should be 0, or if it's non-zero, the symmetry protects it to stay close to 0. Quantum corrections don't blow it up. So this theory would be a theory like that because, well, it turns out as in the limit m squared goes to 0, the theory goes back to GR, which has this bigger symmetry, diffeomorphism invariance, the symmetry group of GR. So that means that that m is naturally small. The smallness of m, we don't worry about why don't quantum corrections create a mass for the graviton in our universe. That's not a question that anyone worries about because it's protected by smallness of m is protected by diffeomorphism invariance. On the other hand, there's this other symmetry in this theory that protects m squared to be close to 3/2 lambda. So together, those two things, if this relation is protected and this guy is protected at a small value, that's saying that lambda is protected at a small value. So the story in terms of finding this theory is that again, Claudia, the person who's visiting this semester, found among this class of theories, among the class of theories with 2 different Vierbeins, and one of them fixed to be, one of them treated as non-dynamical, fixed to be the Minkowski-Vierbein. She found the unique sort of candidate theory within that class that could be this theory, could be the partially massless theory. And so then she and collaborators, Kurt and Andrew and the person Rachel Rosen went through and checked, is it really the right theory? And it comes sort of miraculously close to being the right theory. A bunch of things work beautifully well beyond what you have any right to expect, beyond what you would expect if it was not the right theory. But then at the end of the day, if you go to 4th order, it turns out to not be the right theory. Or if it is the right theory, even that, there might be a caveat. But it appears to not be the right theory, but very tantalizingly close to the right theory. So anyway, that's the story at the moment, is that this class of models is only a few years old. Oh, the other thing is that it only exists, if it exists, it appears to only exist in 4 dimensions. So it would also be sort of a very beautiful explanation for why we live in 4 dimensions, which is another sort of famous unsolved problem in physics. Anyway, I just want to say there's this new problem. It should be getting a lot more attention than it is. I think it's super exciting. You should all, what are we all waiting here for? We should all go off and solve it. Let's end the lecture on that note. I apologize. I didn't get to baryogenesis, but instead of running way over, or should I run way over? Well, could I? Yeah, I shouldn't, right? Yeah, I see that. That's I appreciate your honesty. Okay, so I will do the 15 minutes blast of baryogenesis at the start of the lecture on Monday. See you guys next week.